Hello and good day to you, Dr. Bridge, Dr. Bachoo, and Mr. Jhagroo. I am Lincoln Francis, and I welcome you to my final year project presentation on the drain cleaning robot, also affectionately named the Advanced Cleaning in Drain Device, or ACID. In this presentation, the following will be discussed: the aim and objectives of this project, a rationale for this project, the literature review, testing associated with the drain cleaning robot, the design, process, and constraints of the drain cleaning robot, and the Gantt chart for this project. The aim of this project is to design and prototype a drain cleaning robot for the University of the West Indies, St. Augustine. The objectives of this project include the designing of the drain cleaning robot and selecting the best design, conducting research on current robotic technologies for the construction of the prototype of the robot, constructing a prototype of the robot, and testing and evaluating the prototype's performance. Municipal waste mismanagement is problematic in developing countries. With the increase in the size of cities and towns, resource consumption and pollution will dramatically increase. On a community level, gutters and drains usually bear the evidence of improper waste disposal and do not show signs of slowing down. Robotics lends itself to being a solution to this problem. As laborers, robots are not paid, do not suffer from fatigue or boredom, and are highly productive. And far from just saving money, robotics has created job avenues and niche industries that did not exist until recently. The ongoing proliferation of robots, even in this endeavor, can lend itself to being solutions to other crises now and in the future. Anka Dragan, roboticist from UC Berkeley, defines a robot as a physically embodied, artificially intelligent agent that can take actions that have effects on the physical world. In keeping with this definition, there are components of the robot that becomes indispensable to it. These are the body or its chassis, sensors, a power source, actuators, and artificially intelligent programming. The key design metrics for the drain cleaning robot are based on the expectations that the client, that is, the University of the West Indies, has for this robot. These design metrics are autonomy, compactness, durability, ease of maintenance, affordability, and aesthetic. In order for ACID to be a functional solution, it needs to be able to address its constraints. These constraints are primarily concerned with how the external environment will impact ACID's performance in drain cleaning. Generally, these constraints fall under two categories: environmental and logistical constraints. Environmental constraints typically deal with the presence of water in the drain while the robot is cleaning, moisture in trash, drain cross-sectional profile and how that will differ with the robot's cross-sectional profile, the primary and secondary gutters and how the robot will perform in both primary and secondary gutters, and biotic factors such as rodents, small animals, and even humans. Logistical constraints are concerned with maneuverability of the robots in the gutter and how effectively the robot can turn in the gutter when it takes a corner. In order to evaluate the robot's performance, tests need to be done to measure quantitatively the success of the robot in drain cleaning operations. However, not all the key attributes of the robot are appropriate for testing, such as costs and aesthetics. Tests evaluate the effectiveness of the robot in maneuverability, cleaning, sensing, and decision making. Please refer to the report section on testing for further details. The design process addresses all the key attributes and maps how they are to be realized in the robot. However, due to the COVID-19 pandemic, it is not feasible to construct the drain cleaning robot to its full potential. That is to say, a suitable prototype of reduced manufacturing quality and capability will have to suffice for the tests previously mentioned. The prototype is expected to underperform from the ideal, but would instead demonstrate key functions of the robot, such as its ability to clean and to be autonomous. However, in what follows in this presentation are still appropriate conceptual designs for the prototype, as well as a valid final concept. This is the functional decomposition black box used for designing of the robot. Here, energy, instructions, and municipal waste are inputted to the robot and contained debris output signals to other devices and the user, as well as energy losses are the resulting outputs. This design concept is called G-Truck. G-Truck features ultrasonic sensors to its sides and to its front, as well as conductivity sensors for trash detection. G-Truck also features 4 DC-powered motor wheels, as well as 2 pairs of counter-rotating rollers powered by DC motors. When rollers activate, trash is entered into the body through here and through here. After the trash passes the 4 rollers, it then passes through this flexible member here, which acts like a valve. The robot has tactile sensors in the bin compartment to detect when it has reached full capacity. This design concept is called the Muncher. The Muncher is equipped with 4 DC-powered wheels, as well as ultrasonic sensors to the front and to the side of the robot to enable it to move in the gutter. It will also use conductivity sensors, which would activate other actuators such that the robot will then be able to clean the gutter. After conductivity sensors test for the presence of trash, linear actuators would push and pull on this bracket. The motion of the bracket is guided by tracks cut out into the body of the Muncher. When this happens, trash is then pushed from this area here to the rollers. The rollers will then spin and force the trash into the bin compartment of the robot. Tactile sensors along the walls of the robot will give an indication of when the robot has reached max capacity. This design concept is called convertible. Convertible would feature ultrasonic sensors to its side and to its front to help with navigation in the gutter, as well as conductivity sensors near the base and the roller to enable it to detect trash. When it comes into contact with trash, the rollers would activate and suck up the trash vertically. After trash is picked up by the first roller, it is then redirected to the second roller, which then allows it to be stored in this bin. This design is convertible because whether it is upright or landscape, it would still work as a gutter cleaning robot. This diagram shows the pairwise comparison chart for all the designs in this project. As you can see, autonomy was excluded because autonomy was a feature to be incorporated in all robot designs. These are the results from the pairwise comparison chart. Compactness ranked as the most important key attribute, while aesthetics ranked as the least important key attribute. From the design selection matrix, it can be seen that concept 2 or convertible had the highest weighted total and is thus selected as the final design for the drain cleaning robot. It will be further optimized and developed as this project continues. This is the Gantt chart, which chronicles various aspects of the project with time in weeks. And as you can see, some steps were already carried out, some took longer than expected to complete, and some have yet to be completed. Thank you for your patience and your time, and I do hope that you enjoyed this presentation. I hope to address any concerns that you may have about this presentation in the interview. And as always, do have yourself a wonderful day.